There we go. Okay, so you've gotten the go that you're all being policed. So let's start with the session. So somebody want to type up something, somebody want to ask anything about the subject, and we can get this baddie going. Don't all yell out at once, of course. No, that was the hint for you guys to say something. Fine, I'm going to start singing. That's what happens. I'll tell you guys. Nobody want to type anything up. Nobody have any questions.
Can you give us, oh, sorry. Can you give us an idea what the exam is like? Like, I don't know, like essay questions or multiple choice or how long?
Okay, sure. The exam is designed to be a torture chamber. No, I'm just kidding. Believe it or not, all that stuff, if you check on Canvas, it's always there, so you don't have to worry about it too much. So when in doubt, you can refer to that bad boy. But if you haven't seen the portal yet, the portals are already there. So you can literally log on to Canvas and go search under quizzes because there's no term for exams, and it'll pop up. You can't start it yet, but it's there, and it'll give you all the instructions and all the basics. Right? And so it'll be open for those 48 hours, as I promised you guys, at least for this exam, right? And so starting in, 6 hours from now, it'll open up, since it starts like at midnight technically, and it'll be open all the way until Tuesday at 11:55 p.m. And it's designed to be for 1 hour. So it's going to be open 1 hour only for you, even though you have the entire 48 hours to play with it, okay? And you choose that time. So there's no limitation for that. Just you find your happy time, whether it is away from work, away from school, whatever you find, that's where you can do that. Now, overall, if you want to find out a little bit more about this exam, like I said, you can read up the instructions that we've already posted. But the first exam is relatively simple. It's meant to be a little bit on the shorter side. If you haven't seen that box, it states that it's a 22 question exam, for example, okay? Of which 20 questions, I'm sorry, I should say that, are the ones that count. Remember, I promised you that all my exams will have that 10% additional as optional or available extra points. So that means there's 22 there. And in my opinion, mind you, so because I've done this long enough, the exam probably will run for about maybe 20-30 minutes for you to take in all honesty, but it's meant to be open for 1 hour for you. So tomorrow you get up at 8, decide to take the exam right then and there. By 9, it'll close up for you. If you don't want to do it tomorrow, you want to do it, after the lab tomorrow night or something like that, you do it at 10 p.m. By 11 p.m., it'll close up for you. If not, you want to take it on Tuesday because you want to study a little bit longer, which is perfectly fine. You can open them at 6 p.m. and finish it by 7. It's only that 1 hour, but you have the entire 2 days to pick when you want to take it. And again, it's only going to be those 22. The questions are randomized. They're taken usually from a larger pool of questions. And for this moment alone, simply because of all the challenges that we've been all going through with campus and all these crazy things going on right now, most, not all, most of the questions will be multiple choice for you this round around, simply because I want to make it a little bit easier on you guys right now. And there will definitely be some very short-term questions, short-term answer questions, I'm sorry. And what I mean by that, these are questions that require 1 or 2 words for you at best, and that's about it. There are definitely nothing that requires statements or essays or anything like that. So the format is relatively simple and basic for a couple of reasons. 1, I wanted to make sure you guys have a chance to experience it, but 2, it becomes very complex to try and grade it when you're starting to ask for essays. And at that point in time, it takes a while to grade them, and things get a little bit kind of murky on who gets what points and where. So at least this is all automated, and you get, everybody gets their scores immediately after the exam itself, with the exception of the short-term questions. I have to grade those myself. And you'll know roughly what your score is, maybe plus or minus 1 or 2 questions. So you get your score right then and there, that way you know where you're at. And then once I get the chance to access them within about 48 hours or so, I'll grade the rest of those questions too. And so all the questions, like I said, if you look at them from Canvas or from my instructions on Canvas as well, it's a single entry type of exam, meaning that, you get 1 question at a time, and you enter literally, your answer, which again, most of them are going to be multiple multiple choice. And once you submit it, that's it. There is no going back on these questions. Now, some people usually ask kind of how come, and this is a lot based on this idea of when we're remote, it kind of has a tendency of kind of relaxing some of the rules. And obviously we still want to maintain the integrity of the course. You want to make sure that people are technically not cheating, right? And so that prevents that. That way people can't just go, oh, let me go back around 5 times and kind of check multiple sources and call my best friend and see how many times I can answer it. That's what this prevents. So that's why it's designed that way. So this is kind of the short version of that. This is kind of your first trial into the class to see how well you can handle this type of system. And then we'll go from there. But that's pretty much the big story. About 20 questions for you guys, most of them multiple choice, all single entry. And again, you have 1 hour of room that you can decide from midnight tonight until Tuesday, whenever you want to finish it. Hopefully that kind of gives a little bit of an explanation for that. Did everybody get that part? You can confirm with me. Cool. Sorry, get lots of little thumbs. Excellent. Anything else that might have been left unclear from that I did not mention, or maybe I forgot? Or are you guys okay with that format? Everybody got it so far? Cool. All right, what else? What else can I help with?
Can we go over the structures and functional groups on question 12 for the
Sure. I'll immediately give you my first disclaimer. I don't remember what questions I asked earlier, so you may have to remind me of them, even though you might say question 12. So
it goes over like the hydroxide, and then it wants to know like what functional group, and then on the other side it gives like amino, and then what the structure is supposed to be on it.
Perfect. So no, I'm aware of that. It's more behind. I don't remember what the question asked. I think it's probably one of the ones that asked you to draw them.
That one's to fill in the slots, but then there is like a draw picture on the bottom too.
Yep, that's definitely it. So actually, I'm going to make it a little bit easier because this is one of the questions that was asked earlier as well. So let me kind of regulate this really fast. And I can show you what the earlier group asked during this. And so it came up, and so this is from earlier. And how we're going to do this in this case is that clearly we can't draw them in online. Canvas doesn't have that ability for you to be able to kind of doodle things around. So the best solution that we have is provided with the pictures and you being able to kind of identify them or talk about them more or less. And so the example that we gave you earlier today is I just picked up something randomly online. I went into Google and looked up some structure, and I said, hey, if I were to put this in the exam, I would ask questions such as, hey, look for this particular group, or circle this, or identify this, or click on this, which are the extents of the limits of Canvas. And so the structure over here that we have, which I have no clue what it is, to be honest, you wouldn't have to draw it. It would be there in part of the question. And I would ask questions such as, hey, you mentioned it earlier, what would be a hydroxyl group, for example? And I already have it highlighted in blue from earlier. So allow me to get my little pen over here and kind of go again. Let me see if I can do this and grab this guy. And so if one of the questions says, something like, identify an alcohol or something like that, right? That's the question that would pop up on the exam. You would simply go, oh, it's this guy right there, right? That's as the extent of complexity that you would have in the exam. Alternatively, it could be something like, hey, circle all the functional groups or something, or some variation thereof. Or it could be something like a reverse question. So let me try a different color over here. Let's try green over here, right? And say, identify a methyl group. I apologize for my horrible writing, right? And so you'd be like, oh, it's this guy right there, or something like that. That's kind of what you'd end up doing. And that's truly how evil and ugly that's going to get. Does that kind of help, David?
Yeah.
Cool. Anything else you can expand on that, or you're good?
What's the abbreviation for the amino, like in the form of like the OH? What is this?
Okay, so simple one. Hang on, let me get my little colors again. I like doodling in colors as much as I can. So I could say, look, you know, what is an amino group, right? That was a horrible U. There we go. And so you'd have to find something ideally that would look either like this, which is always the one with nitrogen, right? Or it could be something like this, either in structural or molecular structure kind of formulas. And that would be it. That would be the guy you'd be looking for. And either it'd be like multiple choice saying A, B, C, or D, and then you can find that correct one, or like we kind of showed up a little bit earlier up here, there might be a somewhere where you can select it and write it down. Does that work?
Yep, thank you.
Not a problem. These questions are easy, people. Give me something more challenging. What do you guys are looking for? Let me go back my blank slide, what people are coming up with stuff. What else do you have for me? That question is always entertaining because when people stay silent for me, I start wondering, well, that means that all of you are perfectly prepared and ready and you're going to get 110% in the exam, right? So that means we can all go home and take a nap.
I have a question. So for the triglycerides, it's either 2 saturated and 1 unsaturated fat, or is it like always going to be different?
So that's a really important question, and I don't get a chance to really talk about it during the recorded lectures. So I'm going to just expand upon it. Not that you need to know about it, okay? So let me try.
Okay.
Because one, it's a little bit more information that you need to know for this exam. So let me expand upon that, okay? So what I am going to tell you is the things you should know, obviously, are its structure. And I'm going to go down a little bit more, and its function, right? So those are the things I discussed in the lecture. But what you're asking specifically is more detail than we really need. What you need to know about this guy is the 2 main components, right? So the 2 components for this, I can spell them. It's going to be your glycerol unit, which is a tiny little sugar, basically a little baby sugar, right? And your fatty acid chains. Right? So those are the 2 main components of them, right? Now, I could go and kind of go into my lecture and go pop up these screens or anything like that. I'm not going to do that. I'll just kind of doodle it a little bit easier for me. So ideally, you'd want, this guy is not going back. Hang on. I went to the wrong one. My slide got lost. There it is. That's what I was trying to do. Ideally, you want a tiny little glycerol unit. So I'm going to kind of highlight these with color. Let's go like over here, right? And so you'd have this 3-carbon sugar usually. I'm not going to fill it out. I'm going to leave it here for just the potential of go to O-Chem and leave it at assuming that it's full. And then your fatty acid chains, right? And so it comes with 3 of them just in the same way, but I'm going to change the colors. So I'm going to talk my fatty acid chains. I'm going to draw these in blue right there. And so you'll always have 3 chains attached. And so for example, I'm going to draw one over here. And I'm going to draw another one over here. Got a little lazier on there. And so you have 2 versions behind them that you need to know, which are the saturated version. And then there's the so-called unsaturated versions that usually have these extra double bonds behind them that kind of stick out a little bit differently, that kind of thing. Now, in terms of the detail you were asking, this is as much as I really need you to know. I need you to know that it carries 2 types of fatty acids. So we have our, where did I go? My guy disappeared. There it goes. You have your unsaturated, right, which is what I drew in like light color. And then you also have your saturated.
Sorry to interrupt, but I cannot see anything on the screen. It might be my connection. Sorry. Oh, there. It's just a delay, I think.
There might be a delay too. Keep that in mind. So
Okay. Okay.
take a little
Sorry.
second before my doodles pop up. So,
Okay.
and
Sure.
again, as always, if people need to.
Oh, there it is.
So,
All right.
does that work? Everybody seen that? Am I having any trouble? Again, call me out on these things. I forget that I'm
Sorry.
just kind of doodling around. Not at all.
No, I see the chains now, the C chains or whatever.
Okay, perfect.
Glycerol.
So there's our glycerol. There's our fatty acid chains that I'm attaching there. And that's the structure. To be honest, that's as much as you really need to know about your triglycerides, right? Now, what you were asking specifically was a little bit more detailed. That again, I'm not going to write it so I don't confuse anybody else either. But the numbers actually change. There could be 3 of one kind. There can be 2 versus 1 or 1 versus 2. So there are lots of variations in there. However, one of the most common things that we find in real life, so this is more of application, is that most triglycerides come in a 2-1 combination. It's hardly ever that you'll find, you know, all 3 saturated or all 3 unsaturated fatty acids. Those are only found typically in synthetic systems. So that means people that process these in a chemistry lab, or even in cooking industries, you can actually make those on purpose. But naturally speaking, you don't find a perfect 3 in there for any reason. And those have to do with other things like health reasons and accumulation and arteriosclerosis and vascular blockage and stuff like that. All good A&P stuff you can learn, but not for us. We want you to know that structure. We want you to know that it's made up of those 2 things, right? And then the last little piece that we want you to know about this are their functions, right? And so this is my chance to kind of ask you around if anybody has or anybody remember any of the functions or main functions of our triglycerides. Does anybody have any good ones they can remember if you've already started studying?
Insulation.
Hey, that's a good one. Nice. That was a good time. Excellent. People. Well done.
Shock absorbing as well.
Insulation. There we go. Whoops. And then the last one, anybody? Anybody want to contribute?
Energy storage.
Always energy. There we go.
I got a lot
Those
of
are the things you want to know for that, right? And so there's variations on how I could ask this question, right? I could easily draw a doodle like I did up there and say, hey, what does this guy do? And you can write those answers of insulation, shock absorption, and energy storage. Or alternatively, I could have a question that says, hey, name a macromolecule that is involved in shock absorption. And you go, oh, it's a triglyceride. And that's what you'd select in your exam as your multiple choice question. Okay, so those are the kind of variations that you could see behind that too. So sometimes with a doodle, sometimes with a doodle, depending on how fast I was able to craft that question, right? So those are the big deals behind it. That's as much as I want you to know. Your book does go into a little bit more detail, which is fine. It helps you explain a little bit more for you in this case, but you don't need to know beyond literally what I'm reporting here. The structure, what are its main components, and obviously then the key functions. Just make sure, again, you understand what those key functions are. Because when I'm kind of placing this in the exam, I will talk about them. So my questions won't just be as simple as what is insulation. That just sounds kind of silly, right? But I can say, look for certain organisms, the use of triglycerides for survival during winter, utilize this molecule in what way? You could say, oh, it's insulation in this case. That's kind of what I'm referring to. I'll try and give it a little bit more of an application twist for you guys too, which is why I also encourage you guys to watch the lectures, because usually that's when I kind of expand upon this a little bit more. Before I start asking a little bit more questions, does everybody understand what each one of those does? Your insulation, your shock absorption, and your energy storage. Is everybody clear on those, or does anybody have any questions about them that didn't kind of make sense during the lecture, or are we still okay? Cool, I'm seeing a few thumbses out there, so this is a good sign, but hey, don't feel shy. I want to make sure that everybody's covered. So if you don't understand what these are, then obviously let me know. All right, well, sounds like a good plan there. We'll kind of divert from here. Anybody else have anything else we can talk about? Any other questions that we can clarify? I'll start moving to other slides.
Professor?
What's up?
So when it comes to just the general information of like all the macromolecules and like the complex macromolecules, do we just need to know, like you said, the structure and function of all the different types of macromolecules?
Absolutely right. And so let me go back also to one of my slides for this because we did this earlier as well. There were 2 points that we talked about. So this is from earlier. Things you wanted to know from that O-Chem part, aside from those functional groups that we kind of just mentioned a little bit earlier. The other piece was how to make those, and that was the coverage of the 2 chemical reactions regarding building polymers or breaking them down. And so that meant the reactions of dehydration synthesis and hydrolysis, right? And so that was part 1, but you'll also see somewhere in here that I've kind of also listed those macromolecules. And so you'll notice that I listed the exact same thing. Not only did you want to know the structures, which is what I have highlighted here. Let me put on my little pointer. So it says the overall structure. So no, I'm not asking you to draw those. That's not what's going to happen. But you should be able to kind of visually inspect the structure and quickly say, oh, that's a protein, or that's DNA, or something like that very quickly. And then be able to tell me the properties, the functions, right? And so we just did that for the triglycerides. That was 1 under the fat group, right? So under the fats, we have 3 of those. We had our triglycerides, we have our phospholipids, and then we have our sterols. So you should be able to know for all those 3. And so then you should also know the structure of what a carb looks like and also its functions. Same thing for proteins and same thing for nucleic acids. So kind of the overarching answer to your question, Mako, which is what you were asking earlier, was yes, know a little bit of the structure. So just visually inspecting it just to know what it looks like, and then definitely know the functions. Why are they important to know? And the reason why that is important, why I factually test you on this, so there's no way out of that. I will ask you questions about this, is because we'll see it in all the other lectures that were done from this point on. So this is just the introduction to them, and we'll definitely see them in topic C, D, and pretty much everything else. You'll see me mention these guys over and over and over. And so understanding their structure right now is kind of the intro to that little bit. So definitely study the structures and the functions.
Got it. Thank you.
Not a problem. What else, peeps? What do we got? Let me move on to a blank slide over here again. Anybody else have any cool questions to ask? Fun stuff?
For the chemical reaction part on that O-Chem part on the bottom where it was a hydrolysis, synthesis, and all of that, we only need to know the 6 chemical reactions. We don't need to know what they're used for just yet, right?
Right. And I can't recall when I mentioned it during topic B. And it was the simple idea of when I mentioned them, those 6 chemical reactions that I wanted to cover, mind you, there's hundreds, was that we will introduce them as we go. So multiple of those, we won't see them until much later. Right now, when we saw them in this situation, let me go hunt for the slide really quick. Let me go back to it. Here, we just kind of said, we talked about 2 of those reactions, the dehydration synthesis reaction and the hydrolysis ones. And not sure if you see kind of what I did earlier today. I was kind of symbolizing those 2 reactions in which the reactions that take the monomers and build them into polymers, that was that dehydration synthesis, hence the little yellow arrow here. And then the one that breaks them into the smaller components or back into their original subunits, that was hydrolysis. And that was the extent, that was it. Again, if you can tell me what the reactions are involved for these 2 processes, that's as much as it's going to go into the exam as well. Anybody else on this stuff? This is good stuff. Good, people, good. Try and move back to my awesome blank slide. Anybody else? Anything I can help with? So while you're hopefully coming up with some awesome questions too, I ask this usually in the morning. I'll ask it again. It's kind of important to me, obviously, as we try and develop these courses that are online, and we've quite haven't gotten the hang of it. How did the review guides kind of work for you guys? Are you guys using them? Are you guys ignoring them? Did they help at all? Are they confusing? I want to hear this. You can type it up if you don't want to tell me directly. If you don't want to call anybody out, that's fine. But this is important to me, so I know that I'm not wasting your time nor mine, right? So if they're just dumb questions on a piece of paper that nobody looks, tell me so I don't put them there. If they are being useful, if you guys are getting something of value from them as you prepare for the exam, let me know as well. So, and I do this because, again, everybody has different opinions and everybody has different ways of studying. Some people don't use them at all. So it's important for me to know, am I doing at least a decent job with writing those, or are they crap? So I see the thumbs, I see the comments in there. So thanks for that confirmation. And if there's something that is missing, something that I forgot or I'm not clarifying very well, let me know too. That way I can add those to our review guides as we go. Cool. All right. Appreciate that feedback. What else do we have, people? What else can I help with questions and stuff like that? What else is unclear? What didn't make sense from my lectures? They help at all. Did you fall asleep? It's okay to admit that.
Could you please go over the different bond formations?
I already did, so let me show you back to that slide too, Emily. So give me half a second here, and let's go over here. You guys are asking me the same questions. This is fun. All right, so bam, I already have a slide ready for that one. So when we talk about bonds, which yes, it'll definitely appear in your exams too, is we need to do two things. What are the bonds and how are they made? So those are two separate questions, right? Or two separate topics, I should say, right? And so there's the three bonds that we talk about, which are your ionic, your covalent, and your hydrogen ones that you're seeing on the screen, right? And how they form is different than the bond itself. For example, ionic bonds, which is usually the easiest one to confuse, is ionic bonds, as let me find it over here. Oh, I'm gonna leave my little pointer on top of it, come as a result when two opposite charges attract. So a plus charge and a negative charge kind of come together. That's how an ionic bond forms. That's its formation. However, it's not the same thing as an ion. An ion comes as a result of losing or gaining electrons, which is different. Even though they're related, obviously, they are not the same thing. So two ions form an ionic bond. And so two ions, because they attract towards another due to electrostatic charges, that's how an ionic bond forms. How an ion forms itself is by the loss or gain of electrons, which is the first statement that we have here, right? So that's kind of one of those things you want to pay attention to, right? Same thing applies to the covalent bonds, right? Covalent bonds form as a result of stability. The reason why they come together is because that outer electron shell, that valence set of electrons, and that octet rule that probably all of you remember from good old chem days, want to stabilize. They want to kind of form those pairs and follow that weird octet rule that some of you guys might have remembered back in the day of keeping things in eights, right? And so that's why a covalent bond forms. Now, what the covalent bond is the sharing of electrons. So this bond comes as a result of two separate elements or molecules or substances sharing pairs of electrons. That's what that bond is. So there's a little bit of a difference between what it is and how it forms, okay? Now, there are three that I mentioned in the lecture. You pretty much, this slide kind of summarizes it all of what each bond is. So the ionic versus the covalent. The bigger differences are, again, that one dissociates in water versus the other one doesn't. Those are the big differences. Covalent bonds are always stronger than the ionic ones. The covalent ones never break up, whereas the ionic ones kind of readily dissociate when you put them in water, hence the concept of an electrolyte, for those of you who remember that from lecture, right? And then we had a third one that we mentioned, simply because we talk about it a lot more in topics C and D, are your hydrogen bonds, which happen to be somewhere in the middle of both. They come as a result of molecules that have that have covalent bonds, but because of their structure and how they're built, sometimes their elements kind of pull a little bit more than others, and they get what we call a dipole moment, meaning they get slight electric charges to them. They're not perfectly neutral, so instead they go, mini charges, if you will. And so these kind of baby charges that they develop allow them to also behave like ions as well. So a very, very weak version of that. So when we discuss these, you have your standard ionics, your standard covalents, and you have the in-betweener, which is your hydrogen bond that is based on covalent bonds of molecules that become a little bit more electric, and then they interact through opposite charges. So those are the three you need to know. They definitely appear on the exam also asking. And then usually the other classification that we end up asking is whether they're intra versus intermolecular bonds, meaning they are within, the term intra meaning inside a molecule, which is a little doodle that I did here in blue also. So imagining that the molecule is this giant blue thing, and so the stuff that is occurring is inside the molecule itself. Those are the attractions, right? Whereas an intermolecular one, which is over here down in green, is between different molecules, separate things trying to interact with another. And so here I'm showing two separate little green boxes that are coming together and interacting with one another and kind of coming together. So that's an intermolecular bond. So it's between things as opposed to within things. So hopefully that kind of covers most of that stuff. Again, this is a relatively easy summary slide. And also at the end of my notes of topic B, there's one slide in there that has the same thing, and I just have probably better pictures that I've drawn out with some molecules in there if you want to refer to that one too. Does that help? Does that clarify that for everybody? Does that seem sensible? Anybody? I'm getting a couple of thumbs here and there, so I'm not sure if everybody's confirming this stuff or not. Okay. Any other questions? Did I miss something? But overall, like I said, this is the big deal behind this story today. Cool. Easy. That was an easy one too. Give me more challenging stuff. Come on. Ask me more fun stuff.
Are we gonna do the, is it Koch's postulates at all? Go over that or no?
I'm going to hope, and only because this is probably one of my favorite things to discuss and not record them, mind you. Believe it or not, I assume you're talking about Koch's postulates.
Yeah.
And the reason behind why I say that is because most people have a very fun way of enunciating those, and I'm not going to repeat that. And so it's actually Koch, the way that's enunciated. We're not going to get into that. But what you're supposed to know about that is the fact that that is one of the contributors to our science, to our field, to micro, right? So that's an important contribution to medicine and science. And so this idea to be able to identify pathogens based on the disease they cause. And that's as far as that goes. You don't need to know dates. You don't need to know times. You don't need to know names. Even though it was by Robert Koch, that's fine. But I'm not even going to ask you that ever. I don't deal with names. I don't deal with times. I don't deal with dates. That is for a history class. You guys can take that later.
Okay, cool. Thank you.
Easy, easy. What else? Let's go back to some blank slides over here so I can start typing up some stuff. There we go. And we'll do it over here too. What else seems unclear? What else did the lectures not cover something? Did something seem kind of difficult?
To what extent do we need to know about the microscope for the exam?
You know what? I swear, like I said many times before, you guys are asking the exact same question from the first session. This is hilarious. I wonder if that just means that I suck at covering these things too many times. So, let's go to this one. Let me go find my slide. That's an excellent question too. Hey, this is not working. There it is. And I'm looking for it here. So again, same question that was asked a little bit earlier, right? This is more of a lab question that we deal with. So during the lab practical, we'll deal with those too. But here it was kind of more of an introduction of also important things that happen in history for micro. And that was the invention of the microscope. So no, you don't really need to know the types and discuss all the details behind that. That's what we do in lab. So we leave that for later too. But you should know at least the basics associated with it, which is what I have listed on the slide, right? And so things like what is refraction or the bending of light, more or less, to be able to magnify things, and how, for example, wavelength is the one that plays a role on how to make things bigger, at least to our eyes. We've already mentioned this in lab many, many times, talking about this idea of what part focality is. And then how does magnification occur? That's probably the more obvious question that pops up in the exam as opposed to the rest, is that magnification comes as a result of us having what we call resolving power or resolution. And what that means to y'all is simply this idea of being able to distinguish two tiny little things as separate. So this idea of being able to not blur things out under a microscope. And so things have limits. Not everything can magnify everything, obviously. And so we have different categories of scopes based on that. So we categorize these based on their limitations. Your standard light or compound scopes, like the ones we use in the lab, have a limitation of a resolving power of about 200 microns, meaning that they can't really make anything smaller than that. You can't observe anything smaller than that. Everything becomes a blur. So that's as low as that goes. And then we have our electron scopes, the cool ones, the fun ones, the ones that we get all the fancy pictures in the textbooks. And so those are the two main categories, the scanning one and the transmission one, or SEM and TEM, right? And under those, the limitation to the SEM is about 10 microns. So that's usually about 20 times better than your light scopes over there. And then the TEM is about 20 times better than that in this case. And so that one gives us to a magnification of about half a micron in this case. And so now we're getting into the level of what we call angstroms. And so these are nanometers in itself, and those are usually the size of atoms at that point in time. And that's it. That's really the extent of what we want for the microscope, or more or less the understanding of how it works, rather than knowing little names or anything else like that.
Chris, right now that we're on microscopes as well, just had a question, because on the last question, it was like, which microscope would you use for this scenario? I only had a question because it was like, for the electron microscope, the scanning and the transmission one, you can use on various ones on there, correct? Or is
right,
that...
You're absolutely right. And that's a great question to ask, David, simply because they overlap. I mean, technically, you can use any of these for anything. In reality, it's more behind deciding which one would be best for that situation, right? I mean, we could use a TEM to observe a bacterium, but that's kind of overkill, probably, right? So that question was more or less designed to see if you understand the scopes themselves and their limitations. So if I said, hey, how could you observe, let's see, 3 molecules interacting together, let's say sugar molecules kind of interacting, you wouldn't use a compound microscope. It's, doesn't have that power, nor even an SEM. At best, you could use a TAM, or even better scopes are called atomic force scopes that would do that, right? But it was more behind kind of triggering you to think, to kind of level, engage things, just for this idea of scale. In terms of what's the best answer for each one of them, you can decide those. There was really no right or wrong associated behind that, to be honest. It was more behind you using kind of your logic and your common sense to decide which one is best. So to observe bacteria, for example, which is one of the examples there, or to observe a fungus or something of that sort, you'd probably just use a compound microscope, the same ones that we use in the lab, and that's good enough. Yes, you could use an SEM, probably overkill, probably more expensive than it needs to be, but we just go with the most efficient method for those. That's what that question was all about. Good stuff, people, good stuff. What else? Now, while we're asking those questions and people are coming up with some answers, this is going to be more from my own curiosity as we go. As those lectures are recorded and usually have 1 or 2 different versions in there, so again, it really depends on when I recorded them sometimes. They should be, now feel free to correct me, of course, come out fairly easy and straightforward. Is anybody kind of having any trouble accessing those, or those kind of unintelligible, confusing, they were pointless, anything like that from those 2? Or were they relatively accessible for you guys to watch in your own awesome time, right? So that's part of the reason why we do this asynchronously during these times. So you can take the time to do it. It's still me, I swear. I was behind those cameras most of the time. having either conversations or narrating myself. But if it's not working for you, I want to know so that I can help you guys out with those too. If there's a different version of how I can do that, then please let me know.
So
Obviously,
you're talking about the lectures?
yeah, the recorded ones
Sorry,
that are
I'm so
popping up
sorry.
on YouTube. No,
Okay.
no worries.
Yeah. No,
Yeah.
they're great. So you're talking to yourself the whole time. Like you're having conversations.
Some
with
of them, not all of them.
yourself.
Way back in the origins of my start at Crafton, I had envisioned this was my crazy idea, mind you, that I wanted to have more of a conversation for these videos too, right? Because it kind of gets a little dull if I'm just talking to myself and I don't even have anybody to talk to. It feels kind of boring, right? And so a lot of my students volunteered. And so my students would come during my office hours and we would sit down and talk about these things too. So some of the first ones that are up there, you'll hear other voices in there. I'm not making up multiple voices. I don't have other voices in my head speaking, if that's what you're wondering. I'm sure you all do that. But so some of them started off like that. But with these limitations right now that we can't hang out with other people and kind of work at the labs themselves more often, that's kind of changed a little bit. But they were, again, designed simply because accessibility for you guys. So that Raul just brought that up too, is the idea is you can go in them whenever, right? You can do them at 3 a.m. or while at work, while you're doing whatever your thing is, and you have tons of time for it. And then obviously during these times like this, I can clarify what didn't make sense, right? So the idea is for that. And so if these are not working for whatever reason, or maybe they're blurry or they're not quite as accessible, if for example, somebody needs captioning for them or something like that, I need to know these things so I can improve them too. So, and more often than not, probably the best feedback that I usually got from these is that you can convert those into MP3s if you want to. I didn't have a space for them on Canvas. We get a limitation, but then you can listen to them in your car, wherever you're going. So it worked really, really well too. But yes, if they're not working for you, let me know so I can find a better way to help you guys out too. All right, that was my speech. Anything else?
Okay, really basic question here. I was a little confused between antibiotic and antibacterial.
Great question. That's
Okay.
a fun one. I like that one. Let's see. Let me go change this one. We gotta move up to my slide. Hang in there. I'm managing 4 screens, so sometimes I get lost in my own screens too. So, all right. So here's a blank. Now here's a good point. We're gonna actually start dealing with those in topic H, and a little bit in topic G, which is gonna be like our full-blown first lecture that you guys will get to have with me online. So we'll probably expand upon that a lot more. But for now, let's kind of start with some terminology, right? At least for this topic. So for topics A and B, at least for us, right? Everything else will pop up a little bit later. So the key concept here is that anytime we listen to things like anti, we get this idea of, oh, it's against, which is correct. But we want to dispel this concept of bacteria. So remember, when we're talking about bacteria specifically, and again, topics C, D, and F will expand upon this a lot more. This is one classification of organisms that we're going to look at. Right? So as part of microbiology, that's just one tiny little thing that we focus on. It's common to hear by that, but we have things like, viruses. So that's another topic that we cover in the class, right? So that's another classification. And then let's throw something in here like, say, helminths, so worms, if you will, which we'll talk about again. So what we're talking about here is that microbiology, especially in topic A, we cover all of these just as a quick kind of example. So I think it was SLO, the 3rd SLO or the 4th SLO. I asked you about, hey, what are the things that we cover in microbiology, the ones that are possibilities that could be pathogenic? And all 3 of these, for example, are some of those examples. Bacteria can be pathogenic. Pretty much all viruses are pathogenic. And some worms, for example, can be pathogenic. And so then we hear terms to prevent them. So now again, this is more for topics G and H, so you don't need to know this quite yet. But then prevention behind this and or treatment has a tendency of, this is kind of a little bit more of a gripe that I have with things, and it just kind of bothers me to just even talk about it, is that people misuse the terms. And so the most common one that works is antibacterial, right? And so something that is literally an antibacterial, as its name implies, works, it's specific to bacteria. Now you take something slightly similar, sounds kind of very, very close, which is an antibiotic, right? Which is now the more general term that we use today, also happens to be specific to bacteria. Oops, let's go that. Now the reason why this is now a big deal is because people have a tendency of using the word antibiotic as a treatment for lots of things, and it's not. This is part of our class. This is why we cover it a little bit later, is that antibiotics, per their design, have two key properties. One of them, they're natural. These are made by other organisms. This is made in nature. This is not done in the lab. You don't make antibiotics in the lab, believe it or not. Now, who uses those terms these days? Nobody. Everybody just kind of throws these terms around, and that's where it leads a little bit to confusion, unfortunately. But antibiotics are actually natural. So we produce antibiotics that are naturally fighting against our own bacteria that are trying to colonize us. Other bacteria produce their own antibiotics, and so do, for example, fungi produce antibiotics. Now, the term that is done in the lab, for example, is a slightly different term. When it's synthetic, oops, let me go for there, it's called an antimicrobial. And so at that point in time, we get this idea that it's synthetic. It means that we did it in some sort of cool lab or something like that. Whoops, I misspelled that, my bad. So that's one bigger difference there. And so we kind of stopped using this term antibiotic because we just kind of assumed that it is used for everything, and it really isn't. So let me kind of go with this guy over here just to kind of use it around. Let's change my little doodler over here. It's not working for some reason. There it is. If it wants to listen to me. And so we've kind of stayed away from this term antibiotic, and we started kind of using specific terms for them. So we have our antibacterial that is done specifically for bacteria, obviously. And then we have things like an antiviral, which is designed specifically for viruses. And then we have, for example, the worm example that I have up there is an antihelminthic. So it's designed to be anti-worms, so anti-parasites. So we now have more specific terms to them simply because people kind of over-abuse the term antibiotic. And now as healthcare providers, more than anything else, one of the most common things we get asked for are antibiotics, even though most people don't really know the restriction. Most of the time when people have your classic viral infection, your good old flu, nothing fancy about it, everything that happens there, there are 2 or 3 flu seasons that we get, people still ask for antibiotics, even though they're useless against them because they're designed only for bacteria. So since you have a viral infection, taking an antibiotic literally does nothing. If anything, it makes it worse because now you're starting to kill good bacteria inside of you, right? So we kind of stayed away from that antibiotic term, and now we became very specific of what we make. If you want something to treat a bacterial infection, you have antibacterials. If you want to treat a viral infection, you have antivirals, and so on and so forth. That's kind of where you guys are kind of important in this world, because you guys are the next generation of healthcare providers to help us kind of clarify that, because people are silly and they make silly assumptions. And so it's your job to help them clarify that. So that's kind of an important distinction. Now, again, I cover this a lot more in topics G, H, and a little bit of F in there too, just to kind of mention why do we use these terms. But sadly, especially for those of you who do work in healthcare right now already, you know that people love using the term antibiotic, and it's kind of lost its meaning. So you should know for your instruction and for your practice and for your exams more than anything else, an antibiotic is a natural substance, in this case, that is designed to fight bacteria only. That's it. That's where that kind of definition kind of rounds off.
Are they mostly fungi, like, or is it just not that specific? You know, because I know penicillin, right? That's a fungi. The fungi.
Well, so let's kind of clarify that a little bit.
Okay.
Penicillin, again, this is definitely some fun stories we're going to have during classification lectures. Have. No, not at all. This is part of the fun. Is that penicillin, it happens to be an antibiotic and also happens to be an antibacterial because it kills bacteria regardless. But it's also natural. And the reason how we know, a little bit of history for those of you who remember topic A, is that we discovered that substance from a fungus. A fungus produces penicillin. It's called penicillium. So the organism that produces penicillin is called Penicillium notatum. And so when this was identified by accident, close to 100 years back now, interestingly enough, we discovered that it produced this cool little substance that was killing off bacteria from a natural source. So we took that into the lab, we isolated it, we developed it, and we now start, peddling it all across the world. But it was made by a fungus, so it's made naturally, right? And so it gets the definition of an antibiotic, right? Now, if it's going to be something that kills fungi more than anything else, that's called an antifungal. That has its own name too. So every different type of treatment and drug has its specific name behind that. So we have our antivirals, our antibacterials, our antifungals, antihelminthics, so on and so forth. And again, we'll start discussing those as we go through the rest of the lectures because there's a little bit more nuances in there, some more fun details to know about that. And those are already in the lectures too if you want to go look at those too ahead of time. And I'll be talking about them when we meet in about 3 weeks, fully online too. That's a fun question always. What else, people? What else? What do we got?
Can we recap the formation and detection of isotopes?
Sure, that's a fun one. There's 2 parts that we want to know there. Hang on, let me kind of move this guy one more slide along. There we go. So blank slide. And so this is always an important one to know simply because it gets a little confusing. So let's go with our isotopes. Whoops. Wow. There it goes. So we have our isotopes. And so what's the big deal behind these guys, right? So, so our isotopes have one strict property. So you need to be able to compare them to their original element. So compare them right to the original element. And basically the rule is simple. It's the same element with different numbers of neutrons. That's the key definition that you want to know. Same element, different number of neutrons. Now, to be a little bit more specific, you probably want to add what makes it the same element. That means it's the same number of protons. Meaning the same atomic number. That's the key definition of all isotopes, okay? It has to be the same guy, just with some extra neutrons or a little bit less of the correct amount, okay? So let me kind of move the style of this slide to make a little more sense. There. So I'm like squishing it off to the left so I can do a little bit more doodling off to the side, right? So here we have, that's the key rule. And so what happens is, that's the definition of your isotope, and then it has a unique property. Well, technically it has a couple of properties. Those elements, those isotopes, end up being heavier or lighter than the original element. Simply, again, because they have extra or less neutrons. So they gain a little bit of weight or lose a little bit of weight. That's one property. And then the second property is that not all, but most of them can be radioactive. And so the idea behind that is that it's the tendency for those elements to return to their original element. Weight. So when this happens, a lot of them can release energy. So that's the common thing that occurs, is that you have these normal elements. Sometimes they gain or lose a little bit of weight. And when they want to go back, they can release a little bit of energy doing so. And that's called radioactivity. And so in the lecture, for those of you who heard it or watched it already, you can measure that radioactivity typically through some sort of screen of some sort. That means some sort of film, whether it's photographic film or X-ray film or something like that, or probably the most misused instrument in all of movie history is a Geiger counter. And so those are the two main ways to measure that radioactivity. But to kind of add to the story, it's always to understand that pretty much radioactivity is also one of those terms that is also misused in media, especially in movies more than anything else, because it doesn't mean what you think it means. Most people end up being scared of the term radioactive, even though you're literally sitting on a radioactive chair right now, and you're probably wearing radioactive clothes and you never knew it, right? And so people, when they hear the term, they automatically assume horrible things like monsters and dumb ideas like the Hulk and Spider-Man kind of thing, right? And sadly, that is not true. The entire planet is radioactive as it is, and so we're constantly exposed to these things. Our elements are constantly changing in their weights, and they're not doing anything to us. They're perfectly normal and natural. So there is this misuse in the regular media that people think that it's scary stuff, and it isn't. It's perfectly normal. Aside from 2 or 3 of them that might be really dangerous out there, which you probably will never come into contact in your life, the rest of them are pretty normal and stable. So there's not a lot of worry there. Now, one of the other things you probably want to be familiar with is, again, the calculation associated with this. And that's very, very simple. This one, you don't really need to do any math at all. It's just make sure you can track it. And so I gave you some examples in the lecture. So the first one that I did was always hydrogen because it's easy to work with, right? Hydrogen happens to be our #1 radioactive element, right? Simply because it's our first one, right? And so we know that, for example, the number of protons that it has, not proteins, protons, that it has is 1. It's our very first element in our periodic table, right? We know for a fact that it has 1 electron simply because of that rule of thumb that we always talk about, is that the number of protons equals the number of neutrons, so it only has 1, right? And then neutrons, which it happens to have 0. It has none, at least for this element. And so that's the most common version of hydrogen that exists, basically atomic weight 1 and no neutrons whatsoever. However, hydrogen does have isotopes. And so isotopes of hydrogen, again, same element, same protons, it's just a different number of neutrons. So I'm literally going to copy and paste this just for the sake of it right now. And I'm going to push it over here. And there are versions of hydrogen in which it has gained 1 neutron. So what has happened here, let me kind of show this. This guy, let me change some colors over here so we can plus do with this. There it goes. Is that hydrogen in its more common state has an atomic weight of 1. So basically the weight of the proton over here. But its isotope has an atomic weight of 2. Even though it's still hydrogen. It's just a little bit heavier. That's what it is. And believe it or not, there's one version that actually has 2 neutrons, so it weighs an atomic weight of 3. But it's still the same element. Again, it's still the exact same number of of protons. Let me just establish that. Let me highlight that. Is that the protons always stay the same. They don't change. No matter what you're seeing, it has to be the same element. Okay, that's that key feature. It has to have the same number of protons. That's that key bit, right? Now what changes is the neutrons. Sometimes it has more, sometimes it has less. Now, what will happen is that when it wants to lose its weight, the joke that I always throw behind this, that I don't always do in the lectures, or at least the recorded ones, is just like you right now, probably at home or somewhere hiding with the extra 15 pounds that you gain because of all those donuts that you consume every day, like myself, right? You go to the gym, not that you can go to the gym right now, and go lose the weight, lose some of those extra poundage, you release energy, you release heat most of the time when you're trying to do so. Well, these elements do the exact same thing. They gain some extra neutrons, so when they want to go back and kind of lose that guy and bring it down to its original 0, it releases energy. And so that energy that gets released is called radioactivity. And most of that time, it's negligible. You don't notice it. It's happening all around you. Like I said, what your bed, your pillow, your shower are all literally radioactive, but they're not really doing anything to you. Most of that even doesn't make it through your skin, for example, and nor does this. The radioactive versions of hydrogen, known as deuterium and tritium, can't even make it to your skin, right? And so it's always knowing that it's just a small change in neutrons, sometimes more or less, it really depends. And when they go back, when they return to their original state, they release a little bit of energy called radioactivity. Most of that is harmless, if not close to all of it is being harmless. But again, like I said, 2 or 3 elements out there that are extremely dangerous and could cause you harm. And again, in your lifetime, you're not likely to run into them unless you're a nuclear chemist or a nuclear physicist. So I highly doubt that any of you guys will run into those. And so that's kind of the problem with talking about radioactivity. Most people are here building nuclear plants, and they automatically assume that all their children are going to go grow wings and turn green or something like that. It's far from true. There's no such thing. So you need to kind of relax that idea and help people understand that we use radioactivity as a really good medical tool. And it's very, very safe and very reliable. So keep that in mind. Does that help? Sorry, I probably went a little bit of a half rant over there too. Everybody makes sense behind what isotopes and radioactivity are?
I understand that, but when you said calculations, we're not obviously doing like an actual math problem, right?
No, that's what I said. Nope. Not
Okay,
at all.
sorry, I didn't hear that part. Apologize.
No. It's quite okay.
Spider-Man thing.
Oh, is that the part you focused on? Clearly.
Yeah.
See, this is the problem.
Yeah, nice joking. Sorry.
No, I get it. So the calculation I was referring to here is the fact that you're adding 1 or 2, and that's about it. There's nothing really to calculate. So.
Oh, speaking of more numbers and all that, what about pH? Are we going to go over that eventually? I know it's kind of like if you kind of know the scale, you're good, but are we going to do any math for that or?
Wow, let's go to that slide that I did this morning. And because we did it also. You guys have a very fun pattern of asking.
Yeah, we're predictable.
It is, it really is. And so I like this. This makes my job a lot easier too. This one is a calculation, but there's 2 stories behind this. One, you can do it your classic general chemistry, organic chemistry of using that formula that I have placed up here, which is the negative log base 10 of the concentration of hydrogen ions, which you can do that. I mean, you have calculators at home and on your phone, and I won't stop you. But if you did that, seriously, you're wasting far more time than you need to. Because there's always been a very simple term to do this, and I teach this to all my chem students too when we did that, is that all you have to do is simply count. And what it is, it's a placeholder, right? You need to know the scale, which is what I have over here on the left, right? You need to know what is acidic, what is basic, and what is neutral, right? So above the scale, it's alkaline, below the scale, it's acidic. Fairly straightforward. Most people can usually grasp that fairly easily. But can they calculate to get that number? And that is done, again, with a little bit of ease. Rather than using that formula, you see that I already did this with my students earlier, with the other group of students, I should say. You're all my students. You're all my children. Is that it's a matter of counting placeholders. And so the idea is always count places. That's the trick. And so whatever number you might throw at me, as long as you can count zeros, okay, there. So I just drew a random number of zeros over there, right? All you have to do is don't try and plug this into your calculator. You don't need to. I usually kind of cross the numbers to make it easier in my head. So I just kind of go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you always count the very first time you encounter a full number. And so that is 10. So that means that this is pH 10. Done. That's as evil as that number gets. And pretty much I get the same comment from all my students now, is that why didn't you get that taught during chemistry? I don't know, because chemistry teachers are evil and they don't like you. That's not. It's just a very simplistic way of calculating this stuff. Remember, and you would have known that also if you remembered your log. And so let me go, I lost my little doodle over here. There it is. It tells you it's a log base 10. That means that all you have to do is count zeros or count by tens. So every zero is a 10. 10, 100, 1,000, 10,000, and so on and so forth. So if you can count those in the very last number, you can calculate pH. That's as ugly as that gets too. So let me do this again. Let me just use use a slightly lighter version of green, right? And so if I do something like this, go, okay, just throw a bunch of zeros there really fast. I assume that I don't even need to challenge you to this. You should be able to tell me what pH that is. Anybody?
5.
Yeah, it's 5. Just count the zeros in the last or the first number you encounter. Done. You should have been able to do this from good old Gen Chem days. Anytime you ask those questions, that's all you needed to do. Now, there is a little bit of a caveat that I'll give you ahead of time, not that you need to do it for my class. What if it's not a 1? What if it's a 4 or a 7 or something like that? Then you start getting the numbers in between. So if it becomes 0.2, it becomes 5.2. If it becomes 0.00004, it becomes 5.3 or something like that. That's all it changes. It's still within the same pH range. And I don't ask those questions. I just wanted you to be able to understand the scale of pH. And that's about it. Does that kind of help?
That's great. Thank you.
Not a problem. Anybody have trouble doing the counting usually? Anybody can do the little cross your lines kind of thing? Cool. All right, what else? What else do we have? Is there fun stuff?
So up to you. Viruses are acellular.
That is correct.
Okay, but I think in the book, or maybe, I know in I forgot about your lecture actually, but it seems like there's a gray area there though, because it seems like it's acellular until it gets the DNA. And I don't know if we're gonna go that far into it, but it's a question, so.
Fair enough. No, and it keeps us entertained. And again, if you have better things to do, do your thing. Don't feel obligated. But you've hit probably one of the more sensitive areas for those of us who are microbiologists and virologists, that for the longest time, I feel that this is kind of like a cancel culture of people just hating on viruses. And viruses are organisms just like everything else. But unfortunately, because most people don't understand them, even if you're just a biologist, people kind of separate viruses from everything else we see. And so even in the textbook, you'll see all the cool classifications. You'll see your animals, your birds, your plants and everything else, but you never see viruses thrown in there. And it is because until the last, I want to say good 20 years, maybe a little bit more, we've truly understood how they work. And we realized that, yes, they are organisms just like everything else. They're just more simplistic. And so because they didn't have cells, because they are parasites in reality, because they're obligate parasites, they require hosts, then people just said, no, they're not alive. When in fact, when you look at viruses, and that's topic F2, once we get to that one, that's always a fun lecture to cover, covering viruses, is that we realize that they're far more powerful than what we think. They have a lot of the same unique properties that you and I do as humans, per se, from the fact that they can reproduce, they can evolve, they can target, and things like that that are very unique of things that are alive. But most people don't like to admit that, especially within our scientific community. So yes, we do have our kind of left and right sides of virology, in which some people call them alive and some people don't. I am part of the culture of yes, they are alive, simply because I am a virologist also, and I do follow the material. So, and something that you guys are going to be the very first class, believe it or not, that gets this information is that the last semester was just happening and they didn't manage to get it, is that we now have a fully classifiable system for viruses, fully, all the way that they're included with the rest of the organisms. And so that means that for all of y'all, your books are about to be rewritten again. And so, what is it? Edition 14 should come up with the new concept of how viruses are now reclassified. And so they receive their own, as you probably, for those of you who remember, you go to Gen Bio days, possibly from high school, when you all classified kingdom, phylum, order, family, all that good stuff. Viruses now have that too. And this is the very first time that we can do that, because that information was published at the end of 2019, and it was made available right before we went into quarantine. So this is all brand new stuff that is popping up for us. But yes, our viruses are definitely much alive, and they're far cooler than you think. And if you don't think that they can kick you wherever you don't want to be kicked, why do you think you're locked up at home? So remember that one. So they're far more evil than what we think they are. Anyway, hopefully, like I said, topic F2, we'll talk a lot about that during classification. And then when we get to topic I, when we talk about pathology and immunology in there, you'll hear a little bit more about those two. Good stuff, good stuff. Anybody else? Is everybody okay with the exam? I mean, I know you're all sitting there staring at me. I can feel your digital eyes upon me. Is the exam this easy that nobody wants to ask me anything? You guys are, I got this in the bag. I don't have to worry about it. What's going on? No? Yes? Maybe? Nobody wants to say anything?
I think with the study guide, it's pretty self-explanatory what you're looking for. So
I tried. Yes, definitely. That's why it's meant to do. And so these are more or less meant just to kind of clarify a few things here and there. And so I'm happy to do so. But if if you have the material down, you have a good understanding behind it, go study some more, go relax, go prepare for lab tomorrow for those of you who are going to be with me, especially at 8 a.m.
And literally, like you said, though, that the exam's going to be very similar to the lecture. So if we watch the lectures, we'll be pretty straightforward with the exam then. Absolutely
right. So if you did my SLOs, if you'd use the review guide, you have some of the information from here that I'll end up posting a little bit later once it compiles, you should be more or less set. And unless there's some contents, maybe you missed something here and there, send me an email. Currently, I'm pretty crazily behind because of all the stuff that is going on, that within about 24 hours to 48 hours, I should get back to you too. And remember, you have the exam until Tuesday. Okay, so don't forget that. You can start now or much later if you want to.
Hi, Professor. I just wanted to ask, how detailed do we need to know about the EIDs that we talked about in the lecture?
I love these questions because they pop up so often. It's not even funny. And Bam. So again, asked earlier today, so this is entertaining. The ones that I covered are meant to be examples, right? Part of topic A, which is just a very simple introduction to the field, is to give you two sides. One, that microbes are really good. They help you 99% of the time. And then a very small fraction of them can be a little bit bad and dangerous. And so that last portion of topic A talks about EIDs. And the idea is that one of the reasons why we're in this field of microbiology is because there's this constant new field of dangerous things, literally like we're witnessing what is happening to us right now. And so hence the term emerging. That E part of our EIDs is a big deal. So one of the main reasons why we study micro in this world is because of the EIDs. So I'm pretty sure every single one of you at some point in time within your lifetime has heard of some sort of outbreak, some sort of disease going on, or simply somebody got, some really bad diarrhea from McDonald's kind of thing, right? You've all heard of it at some point in time. And so these are always ongoing infections. So I gave you like 8 or 9 of those at the end just to kind of say, hey, look, these are the current things that are popping up. These are the hot topics of our field right now, and they're only examples. You're not meant to know anything about them because, yeah, we will cover them a little bit later, but it was, are you familiar with these? And if I asked you, hey, can you give me an example or two about them, you should be able to quote any of the ones that I gave you or anything that's popping up around you right now. Now, let's be frank. Nobody wants to hear about coronaviruses right now. It's just overstated at this point in time. So if I ask you that question, give me an EID, don't say that. I might just get mad. But aside from that, there's tons of them out there, right? And so that's what that field is meant. You're not meant to memorize those. It's meant for you to be able to sit to talk about them. And so even in the exams, it's literally for your ability to say, hey, yeah, I remember hearing about Zika. Bam. That's an example of an EID. The example I used a little bit earlier in the other session was a 157H7, which was basically dysenteric E. coli. So this is always your number one classic evil case of food poisoning at most fast food industries. So anytime most people claim that they ate something at McDonald's and had a horrible week, it's this guy. There's a couple more that are culprits, but this one is one of the most common ones. So that's really where that field went. It's meant to be examples to kind of introduce you to kind of show that, look, there's crazy parts of microbiology too. There's good and there's bad. Cool. Danielle, simply because I think people were going away. So if you got the information you needed, they're just kind of, I think, I could be wrong. Maybe I'm self-serving myself in this case. It's more behind, I think they're happy and they're done. That's all. So yes, if you don't have any questions, you don't need to feel forced. I'll post these up for you to review. And then, like I said, I'll see most of you guys tomorrow if you get a chance. All right, I'm going to stop the recording here simply because I'm not getting any questions. And if anybody else wants to hang around or whatever,